The main constituent of steel is the element iron. In its molten or liquid state, the iron atoms move freely. Making steel strong requires precise control of a number of critical factors. They are how the steel is cooled, the steel microstructure, and the chemical composition. As the liquid metal cools, the iron atoms start to pack closely together in a regular arrangement to form crystals. These crystals start in many different places in the melt and then grow until they meet other crystals growing in different directions. The result is a polycrystalline structure. The areas where the crystals meet in the solid metal are known as grain boundaries. Individual grains are very small and usually only visible under a microscope. Iron can exist in two different crystalline forms according to how its atoms are arranged. These close-packed structures are body-centered cubic, known as ferrite, and face-centered cubic, known as austenite. At high temperatures, iron exists as austenite. When it cools below a critical temperature, it transforms to ferrite. The transformation between austenite and ferrite becomes vital when we add carbon atoms to create a strong steel. Austenite allows carbon atoms to fit easily into some of the spaces between the iron atoms. But in ferrite, the spaces between the iron atoms are smaller. If the hot steel is quenched or cooled quickly, the carbon atoms are trapped in the ferrite structure. This forces the creation of a distorted crystal structure known as martensite. Martensite is very hard and is the key reason why steel can be made so strong. No metal crystal, however, has a perfectly symmetrical structure. Instead, we find extra half-planes of atoms that create dislocations, fault lines in the crystal structure. When the steel is under stress, these dislocations move easily through the atomic structure, resulting in plastic deformation. Dislocations make metals versatile and useful. However, to make steel extra strong, we need to block their movement. There are several ways to do this. Grain boundaries are effective barriers to dislocation movement. Smaller grains provide more barriers. The introduction of carbon in solid solution creates internal stresses that resist dislocation movement. You can think of this as the internal friction of steel. Alloying elements form small precipitated carbide or intermetallic particles that can pin dislocations in place. Ovako steels all use these benefits, but the hybrid steel provides an optimum combination of all the strengthening mechanisms. Particles on an almost atomic level are used for hardening the steel. Hybrid steel contains thousands of billions of particles per cubic millimeter. The result is a family of steels that deliver excellent strength, even at elevated temperatures. So now you have seen how steel becomes strong by a precise control of a number of critical factors involving cooling, microstructure, and chemical composition.